Hello guys. So today in this video I shall talk about my interview experience at IIT Delhi. Delhi. So let's start. In IIT Delhi there are actually two phases of the interview. That is first they call you based on your GATE, NET or JEST scores. And then what you do is just let me check the if the recording I have started or not, because most of the times I forget it and later uh, restart the whole video again. So yes, it is working. Okay. So there are actually two phases of the interview. That is, first they call you based upon NET, GATE or JEST score, and then they take the interview. Say they select around 1 in 4. Around this is the ratio they select, and then after you get selected in the first round, you need to choose your guide, that is under whom you want to work with. You have to mail them, and for my case, uh, I had to give a separate interview for that. Okay. So and I performed well in both of the interviews, and I was selected at IIT Delhi for PhD. And so today, but the main interview is the one that is you give in the first round. That is the main interview, and there are many professors are there to take that interview. So I shall talk about that part only today. That is your primary interview that you have to qualify first. Okay. So let's start. So apart from the brief introduction part, I shall not talk about it more, because it is almost all in all the places they are like same. That is what have you done your MSc. I mean they do some initial talks to calm you, that you don't get panicked. So they familiarize with you. Know they want to know about you. I mean, what is your interest, etc., etc. So this part just keep it aside. We are not. Let's get into the physics part. Okay. So the first question, I mean, they asked me that what is my interest. So I said that I am interested in condensed matter physics, or more specifically solid state physics, but in the theoretical part. Okay. So they started asking me. First question was, I haven't. So let me first change it to black. How to change it? Color. I think it would work. I hope it should work. Yes, it is working. So, so first question was, that is, you have a 1D monovalent valent atom lattice. Okay, you have a 1D monovalent lattice. It is metal or insulator? Simple question. So if it is not clear to you, let me just explain it a bit. So we have a lattice. Okay, 1D lattice. It goes like this. So, and these are monovalent. So monovalent means what? That is, it can give only one electron, or it can take only one electron. So for the time being, um, say it is chlorine. Okay, so chlorine. Just take. So I'm sorry, not chlorine. No. Chlorine can take electron, just not chlorine. It will be very bad example. This is sodium. Na. What can sodium do? It will remove one electron from its last s orbital. Okay, so it gives an electron, becomes plus. Gives an electron, becomes plus. Gives an electron, becomes plus. Okay. So this is our monovalent. That is, it can give only one electron per atom. Okay. If it is magnesium, then it is not a monovalent. It is divalent. Okay. So it is sodium. So it is metal or insulator. If we had say such system, So it is not an ideal that ideally we don't get a one-dimensional system. But if we had, then what would it be? So the answer is metal. It would be metal. So why is that? Answer is metal. Why is that? So it is very simple reason that you know the band structure in one dimension. It is, I think you know that the band structure in one dimension look like what? Aha. Sorry. I am not used to writing in my laptop, so there are some bugs. So it looks like this, no? I think it looks like this. So and then there are like these, then again this goes, this continues to be okay. So there it is what? It is our gap, right? It is our k direction, and it is our energy direction. And this picture is in one dimension, and it is in the, I think this picture is called reduced zone scheme. Okay, that is reduced zone mean actually the band structure is like this, and it is also goes like this here, this. But if you just look into this place only, it is in reduced zone scheme. Okay, but it does not matter in what scheme you are talking about. It is just it is our 2 pi by a. It is our first value below in zone. Okay, so because all the things will be exhibit same behavior. So just forget about the technical things. So it is a band structure, okay, in 1D, and it is a monovalent atom. And if you know that these bands are not that they are continuous, they are states here. It is our energy scale. States here. These are states. There are states there. Okay. Now these are discrete states, and the number of the states is equal to number of the states is equal to n. What is that n? That is 1D n atoms. If there are n atoms, then there will be n states here. Okay. So if you are in 1D and you feel and you try to fill these states, then will it be what will be the field state? I mean, what will be the state then? You know, one state can accommodate two electrons, right? One state can accommodate two electrons. One is spin up and one is spin down, and we have totally n states, n electrons. So what will be the resulting configuration? The configuration will be like this. That is, half the states will be get filled, right? Because there are n states and we have n electrons, but sorry, there are n states, but each state gives 2 electrons. So we have 2n total space for the electrons to occupy, but we are only filling the n electrons. So these are empty. These are empty. So when there is a empty states, what does that mean? If you apply external electric field, electron here can take energy and go here, and again it can, and the electron this side can go to there. So electron can move in this region, right? So when the electron can move, it is a metal. Very simple explanation. Okay, now I told him this, and then in he asked me, he wanted to get in deep in that. So he asked me, now we have a 1D divalent atoms, divalent lattice, sorry, not atom, lattice. What will be the state? What will be the it it will be metal or insulator? So simple explanation, it is insulator. Why? Very simple. We can draw conclusion from this state also, this thing also. If we have, it is in divalent, that is each, say it is magnesium Mg2 plus. So each atom is contributing 2 electrons. So if there are n atoms, it will contribute 2n electrons, and we have 2n states. So in this case, all states will be filled. 2n states are filled by 2n electrons. So, and there is a band gap there, right? There's a band gap there. So, and so you can, so usually you don't have, unless you just and unless you give enough high energy, that there is a thing called breaking or something big. I don't remember though, but it is not is usually possible for electrons to go from here to here. Not usually possible in one dimension. Okay, so this is not possible. So you don't have to think like all this. That is now here all the states have been filled. Now electron cannot go here to here from easily. Okay, so it is an insulator because electron experience a band gap here. Like in this case they have a free straight here. He can easily move to there, but here he cannot do like that. So it is an insulator. Now he asked me, he went in more deep. That is what happens in 2D, right? In so he asked me that say the same things, repeat the same thing, same question, but instead of 1D, take 2D. So 2D first 2D monovalent lattice. So what will be the answer? So very simple, 2D monovalent. In 1D, even it is metal. In 2D, it is very expect it will also be metal because the states are still the same. States are still high and the electrons are still the less. So it is metal. But in 2D, if it is divalent, you have to know this, okay? Before, so I knew all these things, okay? So this is some tricky. It is divalent. Then you cannot say that it is a insulator like we did in 1D case. You cannot say confirmly if it is insulator or metal. Why? Because band overlap. I mean, when do we get a metal? When the conduction band and valence band overlaps, right? So in 2D, this conduction band and valence band can overlap, but in 1D it is not possible. In 1D the bands cannot overlap. In 1D bands can never overlap. Never overlap. Possible in it is possible in 2D. In 2D. So you cannot say confirmly that it is a insulator. It may be an insulator, may not be an insulator. When if the bands is overlapped, then it is metal. If the conduction band and valence band is overlapped, it is metal. And if it is not overlapped, it depends on the system. It is a insulator. Okay. So these are the tricky part. And you may ask again that he did not ask me that question, that why it is so that in 2D it can overlap and in 1D it cannot overlap. Why it is so? You can ask that question. So a just intuitive idea I can tell you that it's not that exact. It may also be wrong, but intuitively what I think is take a simple quantum harmonic oscillator. Okay, in 1D the energy is non-degenerate, right? N plus half h cross omega, But in 2D energy is nx plus ny plus 1 h cross omega. It is n plus 1 fold degenerate. That is the first excited state is n is equal to 0, so it will be I mean the ground state n is equal to 0, so it will be non-degenerate. But for the first excited state it will be 1 plus 1 two-fold degenerate. Okay, so in 2D the system is not the same like in 1D. In one like for the electron case you can have like only bands cannot overlap here, okay? But in 2D it is possible that that the bands overlap in some region. I mean okay, let's not get deep into this, but just it is an intuitive idea, that is for the I mean we write the energy dispersion relation is like some E naught plus some constant into cos kx into a plus cos ky into a. It is from tide binding model we get these kinds of expression. That is, it can so happen that for defined values of kx ky the energy is still the same. So it may happen the for the ground, I mean for the ground state the energy and for the excited state the energy is almost same. So though it's not a good, I don't think it was a good explanation, but it can be intuitively you can think like that. In 2D the systems are defined, not in 1D. The degeneracy is possible there. So uh, in 2D the bands can overlap. Okay, the grounds, the uppermost level of the ground state and the lowermost level of the uppermost level of the valence band and the lowermost level of the conduction band can be thought of an equal energy state, can be. Okay, like in this case you can find this that two nx and ny values give the same energy. Okay, so it can be possible there in 2D, though it was not asked me, he did not ask me because he already asked too much question from these things. So okay, now the next question was how to calculate band structure, how to find band structure. I said so much things about bands looking like this, like bands looking like these, etc., etc., etc. How do we know that? How do we know bands look like this? Okay, so there are several methods. I told him that one is, there are several methods. I don't know all of the methods, but what I read in the book, that is we had a nearly free electron model. Nearly free electron model, or like it's like we have b is equal to 0 first of all. Then you add a perturbative field like some v of r is equal to v of r plus r, but we assume that v is very small. The potential is very small, but it is periodic. Okay, and one good example of it is chronic penny model. I hope you have all read this chronic penny model. It is a chronic penny model. We take the v of r to be like this, na. I think so because I have studied this thing a long time back. The potential looks, I think, almost like this, and we and the end we what we do, we this height v naught, we decrease v naught and increase this. I'm not sure. I will not go deep into that. Okay, but this is an example of chronic penny model. Okay, so we can, I mean, chronic penny model is some I mean an an example, but we can also do it for in general for a small v of r, arbitrary v of r you can take, and you can easily find the some perturbative approach. You can find the band structure in how it looks like. Okay, one thing, and we also can do it, this the tide binding approach. In tide binding approach, what we do, the main idea is first of all we say the atoms are far apart, very far apart. Okay, so there is only one the overlap between the energy state is on 0. Okay, then what we do, we bring them closer. When we bring them closer, what happens? What happens is, when there is a one state of the, sorry, I should not draw like this. When there is one state of the single atom, say it is Na plus. Okay, if we bring 2 Na plus very closer, it will split like this. Okay, when we bring n number of Na plus, it will they split like this. Okay, so we get a band, and it will be number of n. Okay, that I said earlier that there are in a band, in this band, there are n states. Why did we say that? If we can find it, we can find it that by using tide binding. We can also find it by using this method also. Okay, but okay, so this method has some approximation, right? So because we use defined blocks theorem or all these things, because it is not an easy task to find and put it for an the band structure for an arbitrary potential. So because the V of R looks very complicated in all the cases. So tight binding model and these are all are some limiting cases. Okay, so these are some approximation, but it is a good approximation. It works in some to explain most of the things. Okay, this thing I said. And okay, so this part of solid state physics was gone. Next he moved to quantum mechanics. Okay, so in quantum mechanics he asked me first of all, I will just state the questions, okay, because I think you already know these things. These are almost these are already very popular questions that have been asked in many places. If you don't know the answer, you can just comment me, and I will explain in some later videos. You can just comment or mail me. Okay, that is in Hund's rule. Hund's rule, you all know. What are the Hund's rule? I will not tell. Okay, just read from books. Any book you can tell. Like I followed the Ashcroft-Marmin. It explains very well. Ashcroft-Marmin or J.T. Lee quantum mechanics. You can read it. So okay. Hund's rule and why? And in the Hund's rule, the first condition for the to find the ground state was S has to be maximum. Maximum. Why? Why S has to be maximum? Then we have this thing he asked me. Okay, now I will also request you to find why that is maybe other place may ask you, that is why L is maximum, why other conditions are prepared, why L then L, why L is maximum, why. So just find these things. You can, these are easily available in market. Okay, so just find it. Then also some popular question like what is Zeeman effect? What is Zeeman effect? Zeeman Paschen-Beck effect. Effect. This Paschen-Beck effect bother me a lot. Let me tell you why. The Zeeman effect we all know, okay, but the Paschen-Beck effect actually I did not know. I mean, while giving the interview, I did not know about Pastenberg effect. But the thing is, I knew. I read that. I knew all the mechanism, but it was, if the book where I followed it, it was not mentioned that it is Pastenberg effect. Okay. Later when I read that, I say that yes. I mean, in so many places that I have given interview, they asked me about what is Pastenberg effect, and I could not tell that. Where I know all the things, what is, I mean, I know the mechanism, what it is done, what in Zeeman effect, what do you do? You part of the system by magnetic field or like this. So I know the mechanism, what the energy state will look like. If someone tell me that but I don't know its name is Zeeman effect, okay, then it will be problematic. So I did not know that it was Pastenberg effect, but it is some related to Zeeman effect, very simple things. You can find it in textbook. So I would suggest reading Griffiths. These are Griffiths quantum mechanics. Very basic explanation has been given there, and in interview you just need to explain the basics, not any advanced thing. Just keep it for research. Okay. So this was done. Whole Zeeman effect, Pastenberg effect. Then another question was like ground state, ground state of hydrogen, singlet or doublet. So actually, the concept of singlet and doublet is not something much clear to me. What I understand is for singlet you have, for singlet, what do you mean by singlet? That is, if you have two spins, then when the spins are paired, right? Like this, in this, or I am drawing this like it's a sorry, because it is some famous thing. It's an eigenstate of the spin operator. So let not get into all these things. When the spins are paired, okay, then it is a singlet. When the spins are not paired, it is not paired. Okay, paired means uh, one up and one down. Okay, it is singlet. And when it is not paired, it is doublet. There are some defined. I mean, I can explain it from here why it is singlet, why it is doublet, but it is not necessary for now. Okay, so in the hydrogen atom, what do we have, and what does singlet and doublet signifies? So say say we have a system like this. It will be singlet or doublet. So it will be a doublet state. Why? Because these are singlet, okay, and singlet state does not break under magnetic field. So why am I saying that? That is spin up. It can take any value. It is also possible, and it is also possible. Unless you are measuring the SZ particle, SZ component, these two are equally possible. So when you apply magnetic field, these two different states gets broken. Okay, so there are two defined energy states. So uh, defined energy states, defined particle, like there will be atoms which have spin in this direction, there will be atom which have spin in this direction. So this will, so two defined energy states will emerge out of this. Okay, so uh, it is called the Zeeman effect, I think. So this is called doublet. You are getting double energy. Okay, and here you will only get the single energy because our spin is zero. Okay, so in the hydrogen atom, what we have? We have only one spin in hydrogen. Okay, so it is doublet. That is what I intuitively think. Okay, it may be wrong because I am not that expert in atomic physics, but my basic knowledge says it should be doublet. Okay, so if you know this thing correctly, you can just correct me. Okay, because I also want to know this thing in detail. But this is what I think. I also told them this, and I mean they did not complain anything, but I'm not sure if it is right or wrong. So everything was going well and till now. Then the last and most trickiest part came. I mean, that is a question in optics. Okay, and the question was very famous question to me. That is difference between double slit, double slit, diffraction, and, and double slit interference. Slit interference. Ference. So it was one of the famous question I said because I thought about this question many times before, but I could not find a concrete answer to this question. Okay, so I found it, but I did not have any answer because but I thought about that question. Okay, but there was no good answer in internet or somewhere or any book. But this is a very basic question. What is the difference? What is the, in both the cases we are using two slits. We are using these two slits, but we are getting different patterns. Okay, so what is the difference? You cannot tell that their pattern is different. Here we get equally spaced, equally intense patterns. Here we get some complicated pattern. It is a very bad and it is the most bad answer you can give in the interview. They are not asking you that. They already know that you know this thing, but what is the basic difference? What causing them to be different? What is the origin? So I told him that, sir, I thought this about before, but I could not find a good answer to this. So the professor who asked me this question, he tried to teach me. Okay, he tried to teach me at the interview. That is this is the most uh, interesting thing about the IIT Delhi interview. They taught me that this question, and that is true from very basics. Okay, he just asked me few basic questions, and at the end, I could answer that myself. That is what is the difference. Okay, so the professor was awesome. I don't remember his name, but he was awesome. Okay, so the first he asked me, that is, what happens if you have a slit and you put light on it. Okay, I said that, sir, we will get a diffraction pattern. Usually, that is, here is high intensity, here we get low intensity, more low intensity. Then he asked me that, okay, let me draw the torch bigger. Then he asked me that you just now broaden the slit, sorry, shorten the slit. Okay, shorten the slit. These are torch. These are very bad torch, though. So you're just shortening the slit. Okay. So what will happen now? It will, it will just broad away, right? I mean, the intensity here will be high though, but the peaks will go much larger. I mean, it will spread more. Okay, if you decrease the width, it will spread more. Okay, now just take this, keep this property in mind, and and actually what happens here is that if you have an intensity like this, okay, sorry, intensity like this, here the if it is 10 I naught, some I naught is some constant. Here it will be, if you decrease the width here, it will be 5 I naught. This will decrease, but these peaks will increase with respect to this. Okay, these peaks intensity will increase. I mean, not, I should not, yes. So compared to this width will increase. So the secondary maxima will try to increase. Okay, when you just decrease that, because the total energy has to remain constant. That is, you cannot make it is 10 I naught and increase this one. So it is not possible. So this will remain, this will decrease, but this will increase. So keep this in mind, and now consider the 2D thing. First of all, you have a broad things. Okay, you are shining light. What will be the happen? We shall get, sorry, we shall get diffraction. I told him all this thing. Okay, because he was just asking some basic question. I will get let me not draw like this. I will get diffraction pattern here, and also diffraction pattern here. Okay, so these are some, these is the diffraction, I mean, double slit diffraction pattern you usually get. Okay, I shall discuss about it later, because he also asked me to draw this separately at the end. So now you start to decrease the width. Okay, now you start to decrease the width. What will happen? That is, these peaks will get smaller and these peaks will get larger, right? These peaks, so at the end, when these are very fine, of the order of the wavelength. Okay, he also asked me that. What I mean, just not go into that. When it is very fine, I mean, when you say it is very fine or too low or too high, you have to specify with respect to what, right? In physics, there is nothing like it is too low, it is low, or it is high. You have to be with respect to what it is high, because there is nothing like infinity. In physics, actually, you have to say in respect to which number 10,000 is like infinity with respect to 10 to the minus 5, but it is not infinity with respect to 9,000. Okay, so with respect to what you have to mention, though. So for the sake of now, it is, say it is very fine. What will be the resulting graph now? So as expected, it will be, all the peaks will be same, right? This is the max. This is the end thing we shall get. And what is it? It is an interference pattern. Interference pattern. Right. So what is the difference between, so, and the order of and how what can I say, how small the I mean how small the slit width has to be, it is order to the wavelength of the light. Okay, you can guess it. That is, it has to be, it cannot be shorter than that. Then the interference pattern will also be disappear. Okay, so of the or of the light, the light's wavelength, incoming light's wavelength. So it is the interference pattern we get. So the main difference in of the diffraction and the interference is in double slit diffraction. Actually, it is not a difference. Interference is a limiting case of a diffraction. It's not different. Okay, when you decrease the slit width, and when the slit width is very small, you get the interference pattern. Okay, you can also check it mathematically. When the I think it is the diffractions, um, the double slit sine square alpha by alpha square into some cos square beta. Okay, where alpha beta are, so if it is your A, that is the slit width, and it is your B, that is the gap between the two slits. Okay, it is actually taken like in the midpoint, or it is like this. Okay, to be precise. Okay, you can approximately say that the gap between this. So then alpha would be, I think, a sin theta by lambda, and beta would be b sin theta by lambda. I'm not sure though, but alpha is proportional to a. Okay, it has to be proportional to a, and when a goes to 0, alpha also goes to 0. Okay, then sine square alpha by alpha square from basic limit alpha tends to 0, it is actually 1. And what do you get? I is equal to I naught, it is actually 1, it is 1. So I naught cos square beta, it is the intensity equation for interference. Okay, so mathematically you can also check that. Okay, but more than the mathematics, you have to understand the physics, why it is happening so. Okay, so just from the basic single slit diffraction, he explained to me so well that I could answer that myself. Okay, so this is the basic difference. So these are the and the I mean these are the long discussion. Okay, these are the very long discussion, the optics part. Uh, because the questions before that I almost answered instantaneously, but these are the because this the part, I mean he asked me part by part question, I have to all answer all the parts, and at the end I could answer the main question myself. So the professor was amazing. So the next part, he just asked me to draw these plots carefully, that is the double slit and single slit diffraction part, and explain them. So I just the single slit looks like this, you all know, looks like this, and the double slit looks like this, and then the missing order, again this missing order, and here similarly like this missing order, and the overlap with a single slit diffraction, right? Sorry for the bad drawing. These are overlap. Okay, I mean it's not like this. It's not like this. Sorry. It's an overlap. Okay. So this, I mean you can study this in books. I mean, not believe in my dirty drawing. So so it is some simple. This is a missing order, missing order. Why missing order occurs, or why the plot looks like this, you can just do some simple mathematics and you can find this. And this thing also, it is very simple. These are some basic things of optics. Okay, you have to know this before giving any Indian interview. The single slit diffraction, in diffraction, single slit or double slit or multiple slits, or interference, Young's double slit experiment. These are some 11, 12. Young's double slit interference we learn in class 11, 12. So I don't think it will be very problematic for you to take a look at these things. So still you can uh, okay. So these are the all the questions that were asked me in the IIT Delhi interview, and I was selected there. And later I gave another interview to a professor that I selected, and that interview also went good. So that was not important. The important part is this, because you all have to give this interview first. Okay, and let me tell you that the professors were extremely good. Okay, don't just panic in the interview. I mean, they help you out. If, and just don't say any rubbish things that if you don't know, if you just what tell them, if you think something, then tell them. To treat them as friends. They are taking an interview just to know you better. Okay, don't think that it is an exam. You have to pass that, but just think like this. That is you have to tell them what do you. I mean, you they need to understand how do you think mostly. Okay, so IIT Delhi interview was one of such interview where the professor also like talked like a friend with me and helped me in the interview. Okay, so it is very awkward that he is helping you in the interview. They are helping you in the exam. So you do so. The main idea is you should not panic. They are there to help you. Okay, so give your best at the interviews. Okay, so in my later videos I shall also talk about my other interviews. This will come part by part. Okay, so if you have any question, please comment in the comment box. And till then, tata, bye bye, have a good time. Okay, bye.